So welcome back, everybody. I hope you've been having a great weekend. Now, the topic for today is mainly going to be about solving differential equations. And I would like to suggest that we, depending on how much time we are left with, that we actually start with convolutional neural networks next week. So that means that we are going to dedicate the day today to essentially to solve differential equations with neural networks. And I'm going to step you through some of the basic algorithms which we have. And we are going to switch then a little bit later over to partial differential equations and see how we can actually program partial differential equations using neural networks. So the essence today is going to focus around this topic, which is a possible topic for the second project. I'm still waiting for feedback from you folks about the topics for project number 2. If there are things which are related to your own research, which you would like us to tailor in specifically to the topics for project number 2. So one variant is going to deal with the partial differential equations and ordinary differential equations. So just to let me give you some quick overview of what the plans are and the resources. So there are several resources in ordinary differential equations and partial differential equations. And there is a recent textbook which you may find useful. And this is the textbook which you find down here. Not this one, but this textbook here. And you can actually download that for free from the Springer website. So the topic which we may have to postpone in order to cover this more properly is the topic about convolutional neural networks. And there as well, there are several very nice resources. There's actually a dedicated course at the University of Oslo, which has its main focus on convolutional neural networks and imaging. So if imaging is one of the topics you are interested in your PhD, I normally recommend to take a look at this course here, IN 5400. So convolutional neural networks are widely used for recognition of images, and it's a huge field in machine learning. Our focus is going to be more on the solution of differential equations, either ordinary differential equations or partial differential equations. So let me just quickly remind you of some of the mathematics we went through last time about differential equations and how we actually end up solving the differential equations when we deal with machine learning methods. So one of the standard basic methods which is used in solving differential equations are based on finite discretization. So the standard methods, and one of them which you may have encountered many times, is the so-called Euler method, and you have the finite discretization is the basic step when we start dealing with the differential equations. And we will do that when we solve neural networks as well. So it means that our x goes over to an x of I, and this x of I is typically given by some x0 plus some I times delta x. This delta x is either defined by you directly, or you would have some x final, which we normally label with an n here. And this I goes from 0, 1 up to n, which is a number of so-called grid points or mesh points. And this is typically given by an x0 divided by the number of integration points. Then we would typically have a function y of x, which is also discretized. In principle, we should actually have changed symbols. So this is given by a y of I. And one of the basic methods is based on Taylor expansions. And the simplest possible one is given by Euler's method. And we went through that one last week. And we're going to use that as a kind of very simple benchmark for the results which we obtain compared with a neural network. So in the Taylor expansion, what you would typically do then is to look at our x plus a delta x or plus minus delta x. And this will be given by our y of I plus minus 1. And this is obviously given by y of I plus minus a delta of x of the derivative y of I plus a delta x squared divided by 2 factorial of y of I. And this continues with higher order terms here, delta x cubed. And the simplest possible method which we have is Euler's method. And depending on whether we look at the backward going or the forward going, we get the explicit Euler scheme or the implicit Euler scheme. And then we have several variants of these types of equations. You can keep improving upon them. You have the whole family of Rumia-Kutta method. You have tons of different ways of rearrange the equations. If you look at the solution of molecular dynamics problems, you will end up with something which is called the velocity Valais method. And these are all methods which are simply based on the possibility to rewrite differential equations in terms of a Taylor expansion. So the Taylor expansion is essentially the basic recipe which you start with. And in this particular case, if you look at Euler's method, we have something which is called the explicit or the forward-going Euler method. And we are going to meet this again when we start looking at partial differential equations. So the explicit scheme simply says that y of I plus 1 is equal to y of I plus a delta x, and then multiplied with the derivative. And then we have obviously higher order terms, which we neglect. So what we end up with is a scheme which runs like this. And then we have the implicit method. So the explicit method is a little bit more delicate in the sense that you can actually show that it will depend on the size of delta x, and you may have delta x values for which it may not converge properly. This leads to something which are normally called stiff differential equations. The implicit method, on the other hand, is based on the backward going algorithm. So you would have an I of I minus 1 minus your y of I. In this case, you would actually have, if you look at the expressions here, which you have up here, you're simply moving this over, and then you're going to get that this is equal to a minus a delta x times y of I. And now we have skipped the high order terms. This means simply that what we have is that y of I is equal to delta x times y of I plus this y of I minus 1. The scheme, the implicit scheme, is normally a scheme which is stable for all values of delta x, and you can prove that mathematically. It becomes a little bit more complicated to use because you depend on the previous step. And when you now start integrating, you actually have to know the value of the previous step. And that means that you will have to need an approximation for the step. When you put I equal to 0, you actually have y of minus 1, which is a point which does not exist. So there are ways to circumvent this one, which we will not deal with here. Our task now is simply to make our first comparison with a neural network. When we looked at neural networks last time, and this is what we're going to dedicate some time to here. So basically, then you have a differential equation where what you're saying is that you have a guess for your wave function as a function of x, or your solution to the differential equation, which is now given by some trial function, IA1 of x, and then you're going to have a new function, h2, which depends on x, but it depends also on the properties of a neural network. So this NN is the neural network, and this will depend on x and the parameters theta of the neural network. So this function which we have here is fully defined by the initial conditions. And what we had up here, this is a new function, which is now our neural network. And theta are the parameters of the neural network. And these are typically the weights and the biases. So we have a slightly different approach to the differential equation. So if we take one of the simplest possible differential equations we can think of. So if you go back to one of the examples which you looked at last time, the first possible example we are going to look at is a differential equation of this type, dy, d of x, which is simply given by minus y times some function y of x. And in this particular case, we know the solution, that the solution of y of x has actually to be given by some initial value, y0, and then we have the exponential here of minus gamma times x, and gamma is just a constant. So gamma is a real constant. So this is a kind of a small, very simple case, but it serves our purposes. And when we deal with neural networks, what we have now is an ansatz for the solution here, which contains the initial conditions, and then the remainder, which is the part which is now going to deal with the remaining part of the solution, which does not necessarily need to obey the initial conditions, because the initial conditions are now fulfilled by this equation, by this function here. And the way we would typically do this now is that we define a cost function . And this is going to be the cost function of d. It's going to be a function which depends on y, on x, and on the parameters theta. And that is given by our d of y dx minus the trial function, which we're putting up here. So now we are going to define this function here. So let's just change it a little bit. So in order to avoid, and I'm going to call this for g, minus g of x. And this g is also being a parameter, function of these parameters theta. And where I now define a trial function, and we want this trial function g to actually be equal to a y. And this trial function g is now given by this h1 of x plus this h2 of x and a function of the neural network parameters theta. So what we're going to start with is a guess for this specific function at h2 and h1. And h1 is typically going to fulfill our initial conditions. So the initial conditions for the system would typically be something like initial conditions. We would have some x0, which is known. And similarly, we would have some y0, which is also known. And with these initial conditions, then we can fix this function h1 of x. So let's take a look at how we can build this up. So keep in mind now that the cost function is actually the difference between the left-hand side and the right-hand side of your differential equations. You would then plug in this trial function, which you have, and then compute the first difference. And then you would try to improve upon this difference by requiring that as you iterate, it should become closer and closer to zero. Ideally, you want to have your cost function equal to zero. So let's switch a little bit back to the slides here now and take a quick look at the way we are going to set up the trial wave function and also define our cost function. So I'm going to go back to the slides here. And please feel free to use the chat function and ask questions if something is unclear. So as we said now, the ordinary differential equation is an equation which now involves functions having one variable. And in our particular case, this function f can depend on the parameter x, the variable x, the function g of x, its derivative, and higher derivatives. So this is just a compact way of writing the difference between the right-hand side and the left-hand side of the differential equations. So we have the initial conditions. So typically what we end up with is something like what you see here. So we have a trial function, which is the one we start with. And then we have a neural network, which is indicated by this function n. This depends on some parameters, p here, and that could be the weights and the biases of the neural network. And then we have the h1, which now defines the initial conditions. So when we are going to optimize now, we are simply going to optimize the difference between the right-hand side and the left-hand side. So the cost function would then typically be given by this function f here, which is the difference between the right-hand side and the left-hand side. We normally take the squared one because it's easier to deal with a squared value than just the absolute value of the difference. So in that sense, you actually magnify the results where you have a larger difference. And this mimics very much what we had when we defined the cost function for standard regression, which is given by the mean squared error. And you see here now that the way you would define a cost function for all the variables n. So now you have the input variables x of I, and the most common situation when you feed this into a neural network is now that you have predefined your integration grid, the x's, as we described in the beginning of the notes on the whiteboard. So we have a finite discretized grid, and the variable x are then predefined by us. So if you use a finite difference scheme, the x's are then values which we are setting up. And that means that we have now an output for every set of x, which defines the function value. And with that, we can now compute the difference between the left-hand side and the right-hand side, and we want to minimize that. So we are simply going to take the derivative of the cost function with respect to these different left-hand sides and right-hand sides. So to perform the minimization using gradient descent, the gradient Cx of P is needed. It might happen that you can find an analytical expression for it, but often it gets pretty messy. And we would typically then use automatic differentiation. So using autograd with either the autograd function, which is now being phased out, you should replace that one with JAX, J-A-C-X, which allows you to include several other functions as well. So automatic differentiation is, as we discussed before the break, is a method of finding the derivatives by using repeated applications of the chain rule with a very high precision. So the first example we are going to look at is actually the example with this simple differential equation, where we have the first derivative, which is simply given by the function itself times some parameter. And in our case, we know the analytical solution here. And that's the one we're going to study now numerically with a neural network. So the program is then going to use a neural network to solve this equation here, where we would have a G0, which is given by this G underscore 0. And then in the example here, I just put gamma equal to 2 and this G0 equal to 10 here. So it's a pretty, as you can see here, it's a pretty simple and dull example here, not very exciting. And we start with a trial solution. And then with that trial solution, we are then going to write a program which sets up everything for us. So we need now, when we're setting up the network, and you can do that using, for instance, TensorFlow, or you can use PyTorch. Here, I'm just going to set up the program itself. So you're going to have a hidden layer. So the program which we have here runs everything with just a hidden layer. And then there's going to be an output layer. The output layer doesn't have any activation function. It simply uses the output from the input from the hidden layer, and that is fed into the output layer, and it just outputs what comes out. So there are n hidden neurons. So that means that what you would have then is something like n hidden, the number of parameters which you have, and times 1 plus the n input layer here. And that's the size of the matrix which is needed in order to set up your design matrix. So the first column in P hidden represents the bias for each neuron in the hidden layer. And the second column represents the weights for each neuron in the hidden layer from the input layer. So if you have n output neurons in the output layer, then the output is given by number of outputs times 1 plus the number of hidden nodes. And that's the size of the output matrix. So the first column represents the bias of each neuron, and the remaining column represents the weight to each neuron. So if we now go and take a closer look at the Jupyter notebook, so let's do that. So let me just bring up that one. And let's go carefully through the program here. So this is the same file, but now as a Jupyter notebook. So let's go slowly down here and set up the basics, the setup of the network. So we're going to reformulate the problem, and we are going to have a function here, which now simply is given by G0. So that satisfies the initial condition. And then I know that this function here at least runs like, if I look at the Taylor expansion of the solution, and now I'm giving to the function here, I'm giving some kind of guidance on the way the solution should look like. So I have an X times the neural network. So this is just a ansatz which I make. I could just have left the neural network find out everything here. And this means that when I take the derivative of the function here, I simply have minus gamma times this trial wave function here. And we want that one to be fulfilled as best as possible. So the minimization problem, as we said here, is now something which depends on the parameters which we have. And that will depend on the parameters in the hidden layer, which would be the number of biases and the number of nodes. And the same with the parameters in the output layer. So this is essentially the kind of function which we now are going to optimize in our neural network for any type of input value X. And the X's are your grid points. So you can now set it up, and basically we end up having to optimize this function here. So we want to optimize this, which is now a function of the hidden and the output nodes. So let's take a look at, we can skip some of these technicalities here, because this is basically going to deal with the sizes of the matrices. And if we now use, and this is just one possibility, you can always change that. So in the example which you will find below here, in the hidden layer, we are using the sigmoid function as an activation function for each node or neuron. So the output from the hidden node is then simply given by this input, which comes from the input layer, and then modulated with the weights and the biases, as we discussed with a standard feed-forward algorithm. And then this is the output from each hidden node, and these are fed into the output layer. So in the output layer, we would then have the biases and the weights for the output layer, and this receives an input from the hidden nodes. And the final matrix, which we would have to deal with, or in this case, it's a vector. So the output vector is simply this matrix here multiplied with what we have from the hidden layer. And then we would use a backpropagation algorithm to update the values for the hidden layers and the output layer, the weights and the biases. And the final thing is actually to use a gradient descent algorithm and then we would update the weights and the biases of the hidden layer and the output layer. So in a certain sense, if you think of a code which you have written for a neural network, suppose you're using either your own code or you have a setup using TensorFlow, what you would end up with then is to decide upon what type of activation functions you want to use for your input layers, for the hidden layer and for the output layer. And then you need to decide upon the type of architecture you want to have, how many hidden layers, how many nodes you want to have in each hidden layer. You have to decide upon the regularization parameter. You have to decide upon the kind of gradient method you want to deal with. And when you have done all this, then it's simply a matter of applying the backpropagation algorithm and computing the gradients. And that is going to be the training of your neural network. So if you look at the code which I have here, I try to make this as simple as possible. So we have a activation function, which is our sigmoid function. In this specific case, we actually calculated the gradient ourselves. And in what would be a better choice is actually to use the autograd functionality. That means the automatic differentiation functionality. And you will see that example a little bit below here. So I'm setting up the hidden weights, the output weights. I define the number of parameters which I have. I define the design matrix here. I'm setting up so I'm simply setting up the input to the hidden layer, which now contains the hidden and the input matrix. I'm giving now the output from the hidden nodes, which is given by the sigmoid function. I have my output layer. This is identical to what we did before. I'm now setting up my trial wave function. So the trial wave function contains this part which reproduces the initial values. I give to it the number of parameters, which are the parameters of the neural network, the weights and the biases. It takes the input value x, and now you see now this is g of x times the neural network. Then I have a function which sets up the right-hand side of the ordinary differential equation. You could actually have made this much simpler if you wanted to. So you can compactify this, but I wanted to just set up the trial function and then the right side of the ordinary differential equation, which is now simply given by this parameter gamma times the trial function. And then I'm setting up the cost function. So I have the cost function here, and now I'm actually using the automatic differentiation to find the derivative of my left-hand side, so which is now given by my trial wave function. And this is given by this function here. And then I'm defining my cost function, which is now my function, which is the trial function, the right-hand side of the ordinary differential equation. And then I subtracted the derivative of the function, and then I square it. And this is my cost function here. And then I simply return the cost function and divide that one by the number of data points which I have. And then when I solve the differential equation, I define my hidden layers, I define my output layer, and then when I run through things here, I now compute the gradients. So I have the cost function gradient, so we need to set up that. And here I have my weights and biases included in the calculation of in the backpropagation algorithm. And I set up the analytical function. I define now the number of these specific values. So I use 10 integration points. This is not an impressive thing. I define simply 10 hidden neurons. I want to do a certain number of iterations. So the code which you see here is not very, how to say, sophisticated. So if you were to use, let's say, TensorFlow or PyTorch or any of these libraries, this would actually allow you the possibility to make a much more sophisticated definition of the neural network. But this is just to show you how you can use a neural network to set up the solution for a differential equation. So keep in mind that the slides here are just meant for, how to say, pedagogical purposes. This is not the kind of neural network you would use in a professional calculation. Then you would typically have many more hidden neurons. You would perhaps have a more sophisticated way to find out how many iterations you need. So this number of iterations is actually the number of backward propagations and forward propagations which you make. This lambda is typically a parameter which you can set up in order to calculate the learning rate, which you see here. This is not fine-tuned, so it's just a fixed learning rate. Keep that in mind as well. And then we simply have a function which we call solve ordinary differential with a neural network. And if you look back, this is essentially this function here. So which implements the back propagation and forward propagation. And then when you have that, you can compare with the analytical result. And you can see now in the beginning, when I have gone through the first forward propagation step, the cost function is pretty large. But then when I've now gone through all the possible iterations, I find a final cost function which is pretty small. So it means that the difference between the right-hand side and the left-hand side is actually not that bad. And the max absolute difference which I have is 0.04. So the function which we solved is a pretty simple one, but you see now that with the right initial conditions defined and a neural network, you can actually solve differential equations. Now, compared with the analytical result, this is actually not, how to say, not that impressive. You can actually get a better precision if you just use the plain, good old-fashioned Euler method. So you can now, if you have one input layer and a specified number of hidden layers and one output layer, you can actually now, if you want to extend the construction of a network into a more general one, you can actually allow the network to contain more than one hidden layer. And the number of neurons within each hidden layer are given as a list of integers in the program below here. So you can repeat much of what you see now and perhaps make it a little bit more sophisticated. So you can define more hidden layers if you want to. So you could have a loop now with more hidden layers. But the basic structure would be the same. So you would have a trial function. You would have your right-hand side, which is given by the trial function times this parameter gamma. But what you can do now is actually to define this for more a deep neural network. So you can have more layers and more neurons. So if you scroll down here, much of the same here is as before, but now you can define a network which has more than just one hidden layer and just proceed and see what happens then. So in this particular case, it's actually not that impressive here, the final result. And it depends very much on the type of problem you're dealing with, and also the way you initialize a network and many, many other things. So another type of example, which we have in the slides here, is a logistic model of population growth, which simply assumes that the population converges towards an equilibrium. And the population growth model can actually be given by a function which is similar to the one we had before, where you have the derivative here, which is given by the function, but now you have a minus g times t. So this is actually a nonlinear differential equation in the unknown function g. In this example, a similar network as the one for the exponential decay using autograd has been used to solve the equation. However, as the implementation might suffer from numerical instabilities and high execution time, this might actually be more apparent in the examples below on solving differential equation. You would normally use a library like TensorFlow. So here we try to stay with a more, simple approach. And we implement for comparison the simple forward Euler method, which we mentioned on the whiteboard notes in the very beginning of the lecture here. So again, you would now have a model of population growth. where the parameters are defined in this specific case. I set alpha equal to 2, a equal to 1, and I simply put this g0 to 1.2. So there's nothing specific about these parameters here. So you will get a slightly different trial function as the boundary conditions or initial conditions actually are different compared to the case for the exponential decay. So in this case here, what you could have now could be a trial solution where you have a g plus t times n of t times p. And there is an analytical solution in this particular case, which is now given by the function which you see here. So you can actually compare the numerical solution with the analytical solution here. And then you can use, in this specific case, we use autograd to compute derivatives consistently. So the network will be similar as the one for the exponential decay, but with some small modifications for the problem which you have here. So you have now the sigmoid function. We are setting up the parameters, which are just defined in this function here. We define the neural network with a number of hidden nodes, the design matrix defined by the input variables here, and then we have the, due to multiple hidden layers, we define a variable which references to the output of the previous layer, which is x previous, which is equal to x input. We define the hidden layers in here, so you can actually define how many hidden layers you want to have. We define the sigmoid function as the activation function again. We define the output layer, and these are just plain definitions. We define a cost function here, and in this particular case, we find the derivatives using automatic differentiation by using this element-wise gradient. And then with the cost function again, which is defined as the difference between the left-hand side and the right-hand side, we will then proceed to evaluate the cost function, and this is the parameter we want, or the function we want to optimize and minimize. The trial function is as before. It's given by, we get the parameters, and it returns a function now, which contains this parameter alpha times the trial wave function, and then this parameter a minus the trial wave function. And then we have this is the right-hand side of the Euler differential equation, and then we have the trial solution, which uses a deep neural network. And that is simply this G0 plus X times this deep neural network parameters. And then we compare with the analytical solution. And finally, we have the function which solves the neural network problem. We iterate back and forth. And as you can see down here, we are setting up the gradients. And now we're actually calculating the gradients using the autograd functionality. And now this gives us simply the gradients of the cost function. And these are the parameters, these are the equations which we need in order to update the parameters of the hidden layers and the output layer. And then we can define then the number of parameters, how many hidden nodes we want to have, the number of layers. We are setting up the, as you can see here, the number of hidden neurons, the number of iterations we want to do, and also the learning rate. So this doesn't need to be, actually, if we want to do this in a more professional way, we would have to have a loop of learning rates in order to find the optimal, the optimal cost function, or actually the function with or the parameters for the learning rates, which optimize the gradients of the cost function. And in principle here, as I said, I mean, the codes are just meant as a way to illustrate how you can set up your own neural network. But what you would end up doing is to use either TensorFlow, PyTorch, or any other library for using neural networks or deep learning methods. Again, here, you would start with a cost function now, which is actually a little bit better. We had a better trial function. And then we end up with a final cost function, which is pretty small here. So we're actually dealing with an error at the 4th digit after the decimal point. And the maximum difference is actually 0.04. which is pretty good for a neural network, which is very simple. And you can also see the comparison between the analytical solution and the solution from the neural network. In our case, we did not have that many integration points either. So you could fine-tune the learning rate. You could fine-tune the hyperparameters, which we haven't done here. So that would be an additional extension of the code which you see. So if you remember back to what we discussed with neural networks, we fine-tuned a hyperparameter. We fine-tuned the learning rate in order to find the best possible either accuracy or cost function. And then we would keep iterating till we found the optimal parameters for the network. But this is, shows you that with very simple efforts, you can set up a neural network with, which solves differential equations with minimal insight about the mathematical shape of the solution. And I think this is pretty impressive. It's also pretty fun. So the only thing we are guiding it with is a neural network multiplied with some parameter x, if you want to guide it, but we didn't need to do that. So the reason why I took this parameter x is that I know that the solution goes like an exponential. So what I'm adding there is actually the first part of the Taylor expansion of an exponential, which is not equal to a constant 1. And then you can use the forward Euler. You can compare that with the neural network. And this is what we described in the beginning of the lecture here, where we are setting up Euler's method. And if you do that, we can then compare Euler's method. So the applications which you see here now is a comparison between Euler's method and the numerical calculations. So if you go down here, you will see a collection of Euler's method, the neural network, and the analytical equation here. And what you see is typically that the neural network now, in this specific case, because Euler's method is a pretty simple method, the neural network is actually doing better than Euler's method in this particular case. You can have other cases where Euler's method is going to do a better job than the neural network. So this is pretty encouraging that with basically no kind of insight about the solution, you're getting rather close to the analytical solution in this specific case here. So we can become, how to say, more and more ambitious, and we can start looking at the second order differential equation. So in this specific case, we can now look at the one-dimensional Poisson equation, which runs like a second derivative equal to a function f of x. And we have now defined a function which lives between x equals 0 and 1. And we have the conditions that g of x is chosen to fulfill. So we have some boundary conditions in this case. So now we don't have initial conditions, but we are plugging in boundary conditions. And that's something which the function, this g0, or this trial function which we defined, has to fulfill. And then you can solve this numerically using programs where you have autograph, or you can also use TensorFlow. And the results from the network can then again be compared to analytical solutions. In addition, it could also be interesting to see how a typical method for numerics, for solving numerically second order differential equations, actually how that behaves compared to this type of equations here. So I would propose now that we take a small break, and just a 15 minutes, and then we continue with now a second order differential equation, but where we now don't deal with initial conditions, but we replace the function with a function now which has to satisfy boundary conditions, and that serves as a way to prepare ourselves for the solution of partial differential equations. And after the break, we're going to look at the type of trial functions which we can set up, and then look at the way we can implement this numerically using neural networks. So I propose that we take a small break. So welcome back. Now, what we are going to look at now is an example of a solution of a differential equation which now contains boundary conditions only. In the previous cases, we were looking at some simpler differential equations, which now contained only initial conditions. And then we're going to use this as a kind of stepping stone towards the solution of partial differential equations, where we will have both initial conditions and boundary conditions. So the boundary conditions are now given by the fact that we have defined a problem where x is defined between 0 and 1. And then we have the values of the function at the boundaries. So the solution we are looking after is this function g. And there is a function which is given by 3x times x squared times an exponential. Now, this type of problem has actually an analytical solution. And if you look closer here at the trial wave function which we are setting in, this has parts of the analytical solution. So we are being guided by the analytical solution here. And the exponential function is now being modeled by the neural network. Now, we may not know an analytical solution. So in this case, what we are doing now is to try to guide the neural network by parts of the analytical solution. Now, if you don't know that, and this is a kind of how to say, a more philosophical discussion on how you use neural networks. So if you think back to what we did in the first project, where we were fitting a polynomial to a certain degree, we knew that the function we wanted to reproduce could be well represented by a polynomial of high degree. So the higher the degree, the closer we would get to the exact representation of the function. And what we were doing then when we did linear regression was that we were feeding in as much information as we could about the equations we wanted to solve. Now, with a neural network, you could guide the neural network by giving it an input about some properties of the functions you want to find. But if you don't know anything, you could now think of going back to this trial solution here and just take away x of 1 minus x, and simply just let the trial function be given by a neural network. So I'm going to invite you to try this out. I'm going to wrap up a tentative version of project number 2, which focuses only on the solution of differential equations. And then one of the things you can play around with is to train your neural network with and without some mathematical insight about the solution you want to deal with. So let me just try to summarize that a little bit before we move on to the implementation of the neural network. And we need to say something about the type of equation which we have. So what we are doing now is to solve a differential equation, which happens to be a differential equation with only one variable. So we have a differential equation here, which is a boundary value problem. In our case, we have a function which is given by the second derivative of x, and this is equal to some function f of x, which in our case had a simple expression which was given by, so this f of x was something which we set as 3x plus x squared times an exponential of x. So this in a certain sense is a problem which we can solve analytically. Now, if you look at the problem which we have, so this x is now defined between 0 and 1. And we would have a solution of g of 0 is equal to g of 1, which is equal to 0. So this is an example of a boundary value condition here. And these are typically called Dirichlet boundary value problems, where you have the function at the two endpoints given by a constant. Now, the way we would proceed in a normal way is to discretize the equations, and we would also set up an equation for the second derivative. So if we now set up the equation for the second derivative, and I assume now that you're familiar with this type of equations, you can actually rewrite that in a discretized form, which is given by g of I plus 1 plus g of I minus 1 minus 2 divided by g of I divided by your delta x squared plus an O of delta x squared. So that means that the mathematical truncation we end up doing leads to an error, which goes like delta x squared multiplied with higher order derivatives. So this function here, let me also remind you of what this g of I plus minus 1 means. This is the same as g of x plus minus delta x. So this is the discretized form, and the way you derive that is to take the Taylor expansions of g of x plus delta x. Let me just quickly remind you of that. So that would be g of x plus g derivative of x times delta x plus g second derivative of delta x squared divided by 2 factorial plus the higher order terms of delta x squared cubed. And then you will do the same with g of x minus delta x. And this is equal to g of x minus g prime of x delta x. And then I have plus the second derivative plus the higher order derivatives. And in this particular case, what you do now is simply to take the difference between the two. Or rather, you actually take g of x plus delta x plus g of x minus delta x. And then if you now skip the higher order terms, this is going to be equal to 2, and I'm setting an approximation sign, 2 times g of x, and this contains plus 2 times, so you can 2 times g second derivative divided by 2 factorial. So this is going to include g of x squared times g of x here. So that means that you can now set up an expression for the second derivative. So what you end up with then, when you look at the differential equation which we have, which is called the Poisson equation in one dimension. So we would have a d second derivative with respect to g of d of x. And this is now given by, I'm putting the equality signs. So it's going to be a minus g of I plus 1 plus g of I minus 1 minus 2 times g of I divided by delta x squared. And this is equal to this function which we have evaluated the value x of I squared. You can now rewrite this one, as you will see in the slides. You can rewrite this one as a set of linear equations, which can then easily be solved by either matrix inversion, or since the matrix you end up with is a tridiagonal matrix, you can then easily set this up as a solution of a linear equation with a tridiagonal algorithm, which is called the Thomas algorithm, which then allows you to quickly evaluate the or solve the differential equation. And you will find the mathematics in the slides here. We're going to repeat that a little bit, and then we're going to compare the calculations of the neural network with the specific mathematical algorithm. So let's go back to the slides, or the Jupyter notebook to be more precise. So let me just stop sharing, and then we go back and go to the Jupyter notebook. So if we go back to the Jupyter notebook, when you solve the equations using neural networks, you actually don't need to do anything. You can now if you have written this code, and I invite you actually to try out these codes, or use TensorFlow or PyTorch if you're more familiar with that, and simply set up the architecture of a neural network, set up the hyperparameters you want to use, the learning rate, the type of stochastic gradient descent method you want to use, the type of activation function you want to use, and simply use TensorFlow to solve the differential equation with a cost function which is defined by the difference squared between the right-hand side and the left-hand side of the differential equation. So in this particular case, we actually guiding our neural network by the insight we have about the analytical solution. But you don't need to do that. So you could try to explore the solution of the problem without any guidance on the trial function. So the only thing you put in the trial function then is a neural network plus either the initial conditions or the boundary conditions. And if you have a partial differential equations, it's both boundary and initial conditions. So here you see a plain repeat of what we had before. There is nothing new here. The neural network is agnostic to the type of trial wave function you're plugging in. You can add more or less insights about the trial wave function. So in this particular case, you see essentially the same. You have the hidden layers which are setting up. You have to set up the output layer. There is nothing new here. You set up your differential equation neural network, where what you're doing now is simply to set up and defining the hidden layers, the parameters of the hidden layers, the parameters of the output layers. You're setting up your cost function, and you're calculating the gradient of the cost function. So, and here I'm using autograd by simply importing the grad function from autograd, which is the automatic differentiation. And then I'm setting up the derivatives, or the gradients actually. And these are the gradients for the different hidden layers. And I'm simply updating these functions as a function of number of iterations. I define my right-hand side of the differential equation, which is this function f of x. I then evaluate my cost function, which now contains the different hidden layers which I want to deal with. It finds a derivative with respect to x of the trial wave function. And then it simply produces again the cost function as you see here. So it's the derivative minus the right-hand side squared. And this is a function I want to optimize. And then it sets up the trial function. It sets up the analytical solutions here. And here we just repeat what we had before. And then I'm comparing the numerical result with the analytical results. So in a certain sense, if you have set up a neural network, and if you're using software like, suppose you're using TensorFlow, or you're using Keras as an API to TensorFlow, or using PyTorch, the only thing you need to specify is indeed your trial wave function. And here again, I'm fixing the learning rate. So this is not an optimal learning rate. You would have to find the optimal learning rate. I'm doing a less number of iterations because I'm actually running a system which is a little bit deeper. So I have two hidden layers here. So I have 200 and 100 hidden neurons. I'm calculating the max difference, which I want to present when I'm done with the calculations. And if you look at my initial cost function, that is pretty large. So my trial wave function is not perhaps the best approach to the exact solution. But when I've run now through the 1,000 iterations, actually my cost function is actually pretty good. So I have an error at the third digit after the decimal point, and the maximum difference between the solutions is also pretty small. So my cost function is rather small, and with this very, very simple neural network without any sophisticated ways of doing the gradient descent. So as you probably saw here, I'm not using a stochastic gradient descent. The implementation here is just a plain, if you go back a little bit here, this is just a plain gradient descent. There is no stochastic gradient descent, which could also speed up your calculations. There is no tuning of the hyperparameters. There is no tuning of the learning rate. So clearly there's a lot of things you can improve in this simple neural network. But if you now look at the comparison on the graph here between the analytical one and the calculation you get from the neural network, you're actually pretty close to the exact results. Now, I mentioned to you that the standard way of solving this type of equation is actually to set up a set of linear equations, which you then can solve easily. You won't solve it by matrix inversion. You can actually rewrite the whole problem as a matrix times the unknown vector, which is the solution, equal to a known vector, which is actually your right-hand side of the differential equation. And the typical way you would proceed in that case is to define a derivative as we did. So we would have the second derivative, which is given by this finite difference formula. And this error which you have here goes like delta x squared. So that's the mathematical truncation error which you have in your finite difference scheme. And the function which you see here, this expression for the second derivative, which we have up here, is actually one of the standard formula for calculating second derivatives. You can improve upon that by having a so-called 5-point expression. So that means you would actually include higher order terms in the Taylor expansion. This is normally called a 3-point formula for the second derivative, because you need to evaluate the function at 3 different points. At the central point, 1 point to the right, and 1 point to the left. So this involves 3 function evaluations. Now, when you rewrite this, you actually get something like this. And then you can obviously plug in the function you want to take the derivative of. You have the boundary conditions, which you have to plug in. And when you're setting up everything and you multiply out this delta x squared, you get the expression which you see here. And this is an expression when you now look at the points where you have the unknown solutions. You know the solutions at the boundary values, and then you can plug in the expressions for the unknown points. And what you would see then is that you can rewrite this in terms of a matrix, which now is a matrix which is tridiagonal. So you have a constant number 2 along the diagonal and a -1 below and above the diagonal. And then we have the unknown quantities here, the g's, and we have the known quantities here, which is the function f, which is the right-hand side of the differential equation, times the step size, which we know. And this is something you can solve easily by simply using an algorithm, which is called the Thomas algorithm. And this is an algorithm which gives a number of floating point operations proportional to the number of integration points you have. And depending on the type of matrix, like in this particular case, the matrix has the same values along the diagonal and the same values along the non-diagonal. This leads typically to 4 times the number of matrix elements as floating point operations. So it's a very efficient algorithm, which you can implement in solving this type of equations. And when you now have the finite difference scheme, you can then proceed and you can set up the code for the solution of the equations using both a neural network, and then you can compare it with the standard differential equation solver. So if you do that, what you have here is simply just a repeat of what you saw before, but where we now set up the matrix, we set up the derivatives, and then we can find the solution with respect to the finite difference method. So what we have now is the max absolute difference between the analytical solution and using the neural network we have with AutoGrad, which gives us an error which is actually the max difference when we now have run the calculations, which is something at the 4th decimal point. Whereas when I do the finite difference scheme, but now I've used a delta x value, which was not too large. So my number of integration points is not very large. I actually have only 10 integration points. And you can see that from also the solution here, that I'm actually operating with 10 points. That is clearly something which I can improve upon if I add more points. And that would improve the numerical scheme here. But with 10 integration points and comparing my numerical scheme, the standard numerical scheme, with what the neural network gives me, I see now that the neural network actually performs slightly better. But you can improve both schemes. The numerical scheme, you can improve that one by having more integration points, and then you would get closer and closer to the exact solution. This difference would actually become much smaller. Whereas the neural network, you would then have to increase the number of iterations. You would have to be a little bit more sophisticated when it comes to gradient descent method. So if you do the timing here, you would find also that the neural network is much more time consuming. So in a certain sense, a neural network calculation here is actually an overkill compared to the standard numerical scheme, which solves these equations here in just some few microseconds. Whereas a neural network takes much more time here in order to converge properly. But the results are pretty encouraging. And if you compare then the numerical scheme and the analytical one and the results you get with the neural networks, these are actually pretty encouraging results. Now, what I should add to this is a kind of a critical remark. The solution of the equation which we are doing now, in a way, using neural network is in a certain sense is a kind of overkill. Now, it has the flexibility that you can plug in a trial wave function, which is given by the neural network. In our calculations, we try to guide the neural network being inspired by the analytical solution. But you don't need to do that. So what we could have done, if we go back to the beginning here, we could actually have said that g of x, the trial wave function, which we have, g of t of x, is simply given by the neural network. So I'm inviting you to try that out and see that whether you can get a similarly good solution, or whether the guidance of the neural network gives a better solution. So this is something to try out. And in the project description, which I'm going to present by the end of the week, you will have to play around with these kind of different types of insights about the solutions which you have. If you don't know much about the solution, you could actually just let the neural network try to find the solution for you. And then to compare that with the analytical solution and to compare it with the standard numerical scheme is something which is very useful to do. And in low dimensions for the system, what you will see then is typically that the neural network will not be able to compete with standard numerical methods. However, when you move to high dimensional problems, where you have 90 degrees of freedom, or you need a high resolution, and where the standard methods may actually have problems in converging properly, then what often happens is that neural networks, they tend to be able to find a solution to the problem without too many complications and too many insights about the problem. But this is something which is not guaranteed. So you would have, there's a lot of trial and error when you're dealing with this kind of approaches. In this particular case, the solutions are very encouraging. But what we're going to do now for the rest of the lecture is to switch to different partial differential equations. So we've been looking at simpler cases now where we just had initial conditions or boundary conditions. Now we're going to have functions of many variables, and then we need to deal with both initial conditions and boundary conditions. And one of the cases we're going to look at is the standard diffusion equation in 1 and 2 dimensions. So I'm just going to list here some of the famous partial differential equations which you may have encountered. And One of the classical one is the so-called wave equation. In this particular case, it's in 1 + 1 dimension. So you have the spatial degrees of freedom represented by x, and then you have the temporal degrees of freedom represented by time t. And a here is a constant. So this is this famous wave equation in 1 dimension, or 1 spatial dimension. And the function u is now a function of x and t. So this function here, to find the solution to it, we need to specify both boundary conditions and initial conditions. Now, what you will find here are many of these famous equations. If you move to 2 dimensions, the same equation changes to a function which depends on x and y and time as well. And then you have the diffusion equation, which is the one we are going to look at. So the diffusion equation in 1 spatial dimension and plus time, or 1 + 1, as we might call it, is simply given by the second derivative with respect to x and the first derivative with respect to time. And a again is a constant, which in this case is just called a diffusion constant. And then we have many, many other types of differential equations. We have a Laplace equation, and then an extension to the problem, which we saw previously, is actually the familiar Laplace equation. Now, notice now that this equation here does not depend on time. And when it does not depend on time, we will only need to specify boundary conditions. We have other equations like the famous Helmholtz equation here, which some of you may have encountered. You have the familiar equations from Brownian motion, which is given by this one. For those of you who done quantum physics, you have the famous Schrödinger equation, which is given by this equation here in 2 dimensions. We have the Maxwell equations. So partial differential equations, actually, they pop up everywhere. So you have Euler's equations, which are given by this, and you may have seen these equations, or you may not have encountered them. For those of you doing a project in geoscience, you may encounter several of these equations here. So one of the equations which are pretty famous ones are the Navier-Stokes equations for incompressible viscous flow. And in this type of equations, solving these equations using neural networks is a very, very interesting field of research. In particular, if you're interested in solving problems like turbulence. And in turbulence, you need often a fine integration grid. And that leads often to complications when you're applying the standard finite element or finite difference methods. And this is one of the areas of applications of neural networks in what we normally call high dimensional problems. We have, in general, what you would have is a differential equations. If you now look at 2 spatial dimensions, you would have different classes of partial differential equations. You would have parabolic, hyperbolic, and elliptical ones. And that depends on the values of these parameters or these functions in front of the second derivatives and first derivatives. So if we now look at the diffusion equation, this is the one we are going to focus a little bit on. I'm not going to go through all the details here. So this functions more the kind of background information. And you have the famous laws. You have Fourier's law, you have Fick's law, Fourier's law for heat conduction, Fick's law for diffusion of particle species. And then you have Ohm's law for electrical condition. But the general equation, if we now scroll down here and try to get rid of all the physical constants, the type of equation we end up solving is something which looks like this. And this constant here is the so-called diffusion constant, and it will depend on the type of problem we are looking at. So if we now take away all the parameters and scale the equations, so these x's and t's are now scaled parameters, which are normally dimensionless, we are ending up with a very simple equation here. And in our case now, we are going to replace t. If we are thinking of Fourier's law for heat conduction, t would then represent the temperature gradient, but we are going to abstract this away and simply replace temperature with a function u of x and t. And we are going to look at the diffusion equation in just one dimension, one spatial dimension. And this is what the equation is going to look like. And we have scaled it away. We have the diffusion constant. And now we are just basically interested in the mathematical scheme here, or rather, to be more precise, the numerical scheme. So I'm going to go through and remind you of some of these schemes. There's one scheme which is called the explicit scheme, which leads to a very simple algorithm, but it is an algorithm which is very conservative when it comes to the values of the discretized steps which we take. So we are going to have a step size in the x direction and a step size in the t direction. So we are going to have now a differential equation with initial conditions. So the function now is given by some well-known property, g of x. And we're also going to have a boundary condition. So if you remember the Poisson equation we had, there we had boundary conditions where we put the boundary value at the x equals 0 to a function, or we can just put it to 0, which is one of the simplest possible choices which we have. And then we have the other boundary point, the other end, at the end point, we would typically then have another function, or we could just put it equal to a constant. So that means that we could have two constants here which are equal to 0. And this is what we're going to implement numerically below here in our examples. So the examples are going to stay pretty simple, but the schemes are general. You would have again defined a step size. You would have a step size in time, delta t, and you would have a step size in x. And now what you're doing now is simply a repeat of what we saw for an ordinary differential equation where we used Euler's scheme. So we apply Euler's method to the first derivative. So that means this quantity here. And then we apply this 3-point formula for the second derivative to the derivative with respect to x. So that means that if you look at this expression here, this equation, we are going to rewrite that in its discretized form. And it's in its discretized form, it's simply going to look like a right-hand side, which now has the second derivative here, and the left-hand side, which simply has Euler's formula implemented for the forward step. And this leads to an explicit scheme, which is very easy to implement, but it suffers from a very conservative and strict constraint on the values of delta t and delta x. But in essence, when you set it up now, when we're setting up the schemes, this is what we end up with. This equation here. So we have one step in time, ahead in time, the previous time step. This is a derivative with respect to time. And this is a second derivative with respect to x. So we go one step to the right, we stay in the center, and then one step to the left. So that means one step back. And then we divide by delta x squared. Then it's pretty common to simply multiply with delta t here. And then we define a new parameter, which is alpha, which is delta t divided by delta x squared. And then what we do next is that we simply rewrite the equations. So I would take this term, I multiply away with delta t. I'm left with this term here. I shuffle that over to the other side. So you see now I have this 1, because I had minus 1 here. That gives me 1 times uij. And then I multiply with delta t, so I get 2 times delta t divided by delta x squared. And this is this 2 alpha. And then I get a multiplication with alpha with these other terms. So this is my scheme. And this is something which I can start solving because I know the solution at time t equal to 0. So that means that if I put j equal to 1 here, j equal to 0, then everything which I have on the right-hand side is known because I know the value of the function at time t equal to 0, and I know the boundary values. So that means that if I put in j equal to 0, and I'm looking after the first time step. So I would have my x values, I, at time step 1. This is given by time step 0, and time step 0. And this is a known function which I now can plug in. And that means that my next iteration in time, so when I go to time equal 2 here, is also something which is known because all the values here can be determined by the previous values. This is why this is called an explicit scheme, because the left-hand side is explicitly defined by the right-hand side. So this is an extremely simple algorithm to implement. And what you would typically do then is that you would simply rewrite this in terms of a matrix times a vector. So you could now say that your unknown values at a time step, j, are simply given by the x values. And we don't include the endpoints. So if you take the endpoints from which are equal to 0 and n plus 1 here, we know the values because we define the boundary conditions to be equal to 0. They could have been given by other values, or they could have been given by a function. That's no complication at all. You would simply have to include them in the equations. When they're equal to 0, there is no point in including them in the equations. And then what you would get is actually something you can reformulate as a so-called explicit scheme in terms of a matrix vector formulation. So you would have this matrix A, and it's pretty easy to see that if you go back to the differential equation here, this matrix A must have 1 minus 2 times alpha on the diagonal, and then it has alpha along the diagonal, the non-diagonals. So this is again a tri-diagonal matrix, and you can actually rewrite this matrix in terms of a matrix vector multiplication, where you start with the first vector, which is given by your initial conditions and boundary conditions, and then you simply multiply it with this matrix here. Now, from a numerical point of view, this is inefficient because a matrix vector multiplication with a matrix which is very sparse is actually a waste of CPU cycles. So what you will be doing here is actually to take and multiply only those matrix elements which are non-zero. And if you go back here, instead of performing a full matrix vector multiplication, which requires n, if the matrix is of dimension n times n, and the vector you're multiplying with has a length n, this requires n squared floating point operations. So if you, on the other hand, instead of doing n squared, you simply perform these multiplications here, it means that for every value of n, you will have to perform three multiplications and 2 additions. So you end up with something between 5, 6 times n floating point operations instead of n squared floating point operations. So you would actually perform the explicit multiplication of those elements which are non-zero. You would not write it in terms of this compact matrix vector operation. That would not be very efficient numerically. But the explicit scheme is extremely simple to implement, as you can see here. You define the boundary values, put them to 0. The new value has also to fulfill the boundary conditions. And then you would have a loop over, you find the new x values, you calculate the function value, and then the discretized update here. So this will be your initial condition, as you see. So you're setting up initial conditions and boundary conditions. And then you have the time integration. So you loop over time from not time equals 0, but you start at time equal 1 to the final time. And this is essentially what you end up doing. So if you do the counting here, you will see that you have 1, 2, 3, 4 floating point operations. And if you have pre-calculated 1 minus 2 alpha, you actually only have four calculations for every value of I, which means that if you have n values, you end up with 4 times n calculations. And then you have 1, 2, 3 vector lookups. And then you have an update to a vector. So you would have 3 lookups of elements of your matrices or your vectors, and 1 update of a vector. So these are the total operations which you will be doing. Now, the problem with the explicit scheme is that it has a very delicate balance, a so-called stability condition, which simply requires that delta t divided by delta x squared is less than or equal to a half. And that clearly puts severe constraints on the possible choices of delta t and delta x. The implicit scheme, which is another way of solving this equation, gives you a stable solution irrespective of values of delta t and delta x. Now, your errors are going to go like functions of delta t and delta x. So that means that the values of delta t and delta x will clearly be important for the final numerical precision. But the implicit scheme is a scheme which is stable for all possible values of delta t and delta x. Whereas if you take the explicit scheme, which is so easy to implement, that has a more severe constraint on the stability of the solution. If you violate this stability, you will actually get numerical results which, after some few time steps, they will either diverge or they will simply just give you basically wrong results. Now, I'm not going to go through all the details below here. You can take a closer look at it. I've added, for the sake of completeness, more information about the implicit, the explicit schemes. And I was thinking that what we could do in project number 2 is actually to look at the comparison between these schemes and the solution with a neural network. So if we now go to the neural network, the problem we must solve now is pretty similar to what we did for the ordinary differential equations. We must have a trial function at hand, but now the trial function would depend also on not only the x's, but also on time. So we need to augment the type of trial wave function which we have. And then when we're done with that, we need to set up a cost function again, which would typically be the difference between the left-hand side and the right-hand side. So in our specific case now, we would have different derivatives. And if you look at these derivatives here now, they could also be derivatives which depend on time. So x, I, x2, and so on here, they can now represent different variables. So if you look at the diffusion equation, if you now take that specific case here in one spatial dimension, what we would have would be something like this, as we discussed above. Now I replaced my u with g here just to indicate that this is going to be my trial wave function in a neural network. We need to find the initial conditions. So when we are setting up the network now, we can actually repeat many of the same things which we did before. So the program will evaluate the network at each possible pair x and t, given an array for the desired x values and t values to approximate the solution now. So the main complication now, compared to what you had before, is that you don't have only one variable, you have two variables. But that is, in principle, that is no complication for a neural network. And basically what you will see here is a simple repeat of what you saw before. And then you can set it up using AutoGrad. But now you would have to have a trial wave function which fulfills the initial conditions and the boundary conditions. And the way you could do that, to fulfill these conditions, you could now have a function h1. If you now look at this function here, this is actually a function which fulfills your boundary conditions and initial conditions. Now, there's one thing you have to be a little bit careful with, and that is the evaluation of the Jacobian. So you need actually to evaluate the Jacobian now, because you have a function whose derivative and whose trial function, you have to take the derivative with respect to both x and t. So this is the complication which comes up now. And in compared with the previous calculations, you need actually to set up the Jacobian, because to find the second derivative with respect to x and t, the Jacobian can be found for the second time. The result is a Hessian matrix, which is the matrix containing all the possible second order mixed derivatives of g, which now is a function of x and t. So I see my time is running out. So next Monday, I'm just going to try to wrap up this discussion on the diffusion equation. And then we are going to move into convolutional neural network and classification problems. By next Monday, I'm going to have a first sketch of project number 2 with differential equations. But I would like to invite you, all of you, to think of other possible variants for project number 2. So as I said, this project is a project where we can really tailor the type of investigations to the research which you are interested in. And obviously one type of research direction is the solution of differential equations, which pop up in many science applications. And neural networks have been shown to be extremely powerful tools in solving complicated problems. However, I know that many of you are also interested in classification. And that is something which we will discuss in more detail next week when we look at convolutional neural networks. So the project number 2 has, as you probably have seen now, there is a possibility to design that according to your needs. So please do come with ideas, inputs for what you would like to do in project number 2.